Did you ever wonder why most of our favorite animals tend to be mammals? My favorite animal is usually a mammal, whether it's a cow I'm milking, an elephant I'm watching, a bear that's watching me, or a dog I'm training. Maybe you've watched a favorite mammal, like a deer, a squirrel, or a family dog or cat, around the home, in a park, zoo, or nature reserve, and wondered, why do mammals look and behave the way they do? Mammals are vertebrates, animals with a spinal cord and a bony spine. Among the vertebrates, there are about 30,000 species of fish, over 8,000 species of reptiles, and almost 10,000 species of birds. And only about 5,400 species of mammals, according to Smithsonian's Dr. Don Wilson and Bucknell University's Dr. Deanne Reeder, who created the most authoritative list of mammals called Mammal Species of the World. The fossil record tells us that mammals evolved almost 200 million years ago and lived as small creatures side by side with dinosaurs until the dinosaurs went extinct about 66 million years ago. Then the mammals exploded onto the scene. Today's 5,000 plus species are assembled in 26 orders in dozens of families, about 30 families in the large rodent order alone. Our knowledge of the mammalian class is ever changing and expanding, because mammalogists continue to find exciting new information from modern molecular evidence, changing our understanding of many existing phylogenetic relationships. For example, in 2015, scientists at the British and American Museums of Natural History published an analysis of the fossils of a mysterious mammal, fossils that Charles Darwin himself had brought back from his voyage to South America on the Beagle. This mammal had gone extinct 10,000 years before Darwin discovered its bones. Yet these scientists were able to extract and analyze the bone's collagen. They found that the collagen from this mystery mammal is most like that of collagen in modern horses' bones. And thus, the researchers were able to demonstrate that Darwin's many extinct mystery ungulates from Argentina and Uruguay were part of the perissodactyl group, the same large group of placental mammals that horses, rhinos, and tapirs belong to. Our modern phylogenetic analyses are even giving us new information about the most common and well-studied groups of mammals. Even skunks, which used to be placed in the carnivore order's weasel family, have now been placed in a new family by themselves, the Mephidae, named after the Latin word mephitis for stench. Despite the fact that there are fewer species of mammals than birds, reptiles, and fish, we have studied many of the world's mammals more intensively than other creatures, perhaps because they are most like humans and our domestic farm livestock. Many things make our fellow mammals distinct from other animals, but the two unique traits of mammals are hair and milk. The technical definition of hair is a filament made of keratin protein that grows from follicles in the skin. Keratin is a major structural protein in all vertebrates, found in skin and claws, hooves and nails, as well as in hair. Although hair seems very delicate to us, keratin protein is one of the toughest proteins an animal can produce, and hair is unique to mammals. Although many groups of animals produce keratin, only mammals turn that keratin into hair. Hair is important to mammals for a number of reasons. They use its form and color patterns for displays and for camouflage. They use it for its insulating properties, for self-defense, and even as a sensory organ. We don't really know when hair evolved, because it is rare in the fossil record. But zoologists do think that hair coincides with the evolution of warm-bloodedness, or endothermy, the ability to produce our own body heat, because hair is a very good insulator. If you spend a lot of metabolic energy producing body heat, it is most efficient to retain it rather than lose it to the environment around you. Unsurprisingly, Arctic animals have a lot of hair for insulation against the cold. For example, zoologists have estimated that the Arctic fox has tens of thousands of hairs per square inch. That's a lot more than I have. With deep underfur and plentiful guard hairs on the outside, The small, non-migratory Arctic fox may be the best adapted of all Arctic creatures for cold temperatures down to 40 below zero or lower. Other Arctic animals, like polar bears and caribou, have thick coats of hollow hairs. These insulate like our human winter parkas that have synthetic hollow fiber filling for efficient protection against deep cold. Arctic foxes also use their fur for camouflage. They are the only members of the Canidae family, that is, the dog-like carnivores, whose fur changes color with the seasons. In the winter, it is pure white to blend in with the snow of its tundra habitat. For summer, it sheds its white fur and replaces it with a brownish or grayish coat that blends in with the tundra grasses. This is useful because the Arctic fox sits at the middle of the food chain. It preys on small animals like rodents and fish, and in turn, it is preyed on sometimes by wolves and bears. Its seasonal coloring disguises it from both predators and prey. Other times, an animal may use its fur for the opposite purpose, to be better seen. The classic example is the lion. Lions are the only members of the Felidae family, the cat-like carnivores, that have visible sexual dimorphism. In other words, there's an obvious visual difference between males and females, and you know what it is, right? Male lions have manes. The mane is not just a signal of maleness. The color and size of a lion's mane is actually influenced by its sex hormones, including testosterone. Research indicates that lions with darker, thicker manes have higher testosterone levels. And not only that, lionesses prefer males with big, dark manes. So a mane gives a lioness information about a lion's ability to survive and reproduce. I said earlier that hair is unique to mammals, and I should also add that all mammals have some form of hair. Now you may be thinking, wait a minute, dolphins and whales are mammals and they're hairless. But in fact, although they look hairless, they do have a few small whiskery hairs on their chins. Elephants look hairless from a distance, but in fact they do have hair, which is more obvious in juveniles than adults. Baby elephants are often redheads with sparse but easy to spot hair on their heads and backs. Adult elephants have much less hair, but it is coarse and black. It's easier to spot on the tips of their tails. In fact, hair takes on many forms that might surprise you. Many mammals have defensive structures made entirely of hair. Porcupines may be the most famous example. All porcupine species are slow and lumbering, which might make them vulnerable to a faster predator. But to make up for their lack of speed and agility, they have strong barbed quills that are really enlarged, modified hairs. And these quills are very painful and difficult to remove, so most predators learn quickly to avoid porcupines. In a similar way, the spiny covering of hedgehogs and the horns of rhinoceros are made of keratin, the same substance that hair is made of. Modern research has busted the old myth that rhino horn is just a clump of dense hair. CT scans and other analyses show that rhino horn covering is more like a horse hoof than like Rapunzel's long hair. Note that rhinos also have hairs on the outside of their bodies like other mammals. Specialized whiskers on cats, dogs, and other mammals are also modified hairs. Whiskers are technically called vibrissae, and they work as sensory receptors. Cats and mice use these sensitive whiskers in the same way we use our fingertips to feel our way around in the dark, to find one another, or to avoid enemies. There is a sensory organ at the base of the whisker called a proprioceptor, which sends tactile signals to the nervous system and the brain. The proprioceptor relates the position of the body and limbs or head, which is important for an animal to be able to make quick decisions for the next movement. They can help an animal figure out if it can fit into a tight space, and can even sense air movements, which probably helps running predators respond to changes in prey movement. Some domestic animals have long whiskers, curly whiskers, or whiskers in strange places like the upper lip, chins, or even ears. Some people apparently feel that they should trim these whiskers. But without these specialized sensory hairs, the animals can become disoriented, frightened, and stressed. So animal whiskers should be left intact. So hair is the first identifying trait of a mammal. The second is the ability of female mammals to produce milk. As we discussed earlier in the course, most mammals, except the egg-laying platypus and echidna, give birth to live young. But some reptiles and fish also give birth to live young, so giving birth to live young is not a unique mammalian trait. As we know, some pigeons, flamingos, and penguins feed their young a secretion from their crop called crop milk. But this secretion has a solid, cheesy consistency, and both sexes produce it. In mammals, milk is liquid and is only produced by the mother from specialized glands. The specialized glands that produce milk are called mammary glands, and female mammals invest a lot of energy providing extended care for their offspring with this special nutrient. To take an extreme example, a baby humpback whale drinks up to 130 gallons of milk each day. Well, I'm not sure how to follow that. Smithsonian's National Zoo scientists have developed the largest milk repository in the world by working with other zoo professionals and gathering this remarkable substance from many species whenever the opportunity presented itself. Much of our knowledge about the milk of other species was developed through studies of milk in zoo-based repositories, because the milk of different species is available during well baby checks of zoo mothers and babies by zoo veterinarians. The Smithsonian Milk Repository alone has almost 6,000 milk samples, and nutritionists and veterinarians have analyzed it to help hand-raised baby animals, including the baby porcupine that wouldn't nurse until banana was added to the milk. Deborah Ben-Shal, a physiologist at Hebrew University and biologist at Jerusalem's Biblical Zoo, started comparative milk studies with a 12-year intensive analysis of different species' milks, from squirrels to zebras, as well as published studies of other species' milks. She published her huge comparative analysis in the International Zoo Yearbook over 50 years ago. Ben-Shal initially thought milk composition would be related to evolutionary relationships among species. For example, the expectation was that all the members of the Ursidae family, all the bears, from polar bears to pandas, would have pretty similar milk composition. Instead, she found that nursing behavior and species ecology determined the main differences in percent fat, protein, and sugar from species to species. Smithsonian's Olaf Oftedal and colleagues performed other major reviews of milk during the 1980s and 90s, and found again that behavioral care, the environment, and additional traits like body size influence the composition of milk in different mammalian species. The composition of milk depends on whether the baby is born in a helpless, altricial, or relatively more advanced precocial state, and on the mother's physical condition and current environment, and on whether young nurse on demand like marsupial or primate babies and precocial hoofed animals that follow their mothers, versus animals that suckle on a schedule like lions or deer that are parked while the mother searches for food. Suckling patterns differ between mammal groups. I found in some field studies that small South American deer, like the pampas deer I study, may suckle their young for 60 to 90 seconds every few hours if they weren't disturbed. If they were disturbed, the suckling bouts would be farther apart and would often last longer. A general rule is that suckling young on some schedule is typical for parents that separate from their young for extended periods. Often these periods of separation are thought to be an anti-predator adaptation. Tree shrews park their tiny babies in secluded nests for 2 days between feeding bouts, and their milk has a relatively high protein and fat content. Wild rabbits park their altricial babies in fur-lined nests and return only about once daily to suckle their young. And rabbits have milk content of over 10% milk protein and over 12% fat. Rabbits and tree shrews are on one end of a parental contact spectrum that extends to the extensive contact of infant-carrying primates in nursing on demand. Some milk biologists call this the strut and suck form of parental care. Among the strut and suck species are humans, whose babies naturally nurse on demand. We have one of the most dilute milks, with low percentages of milk proteins at 1% and fat at about 4.5%. Dairy cow milk is fairly similar to ours, with a little bit more protein and 3.5% milk fat in Holstein milk and 5.5% milk fat in the milk of the Jersey cow breed. That's probably one of the reasons many of us can digest it. The relationship between mothers and infants and suckling bouts can also influence conservation activities. In my own studies in Uruguay and Argentina, I found that the endangered pampas deer had a month-long birth peak around springtime, and their fawns are hider fawns that spend their first 10 to 15 days hidden under grassy clumps that females only visit every couple of hours. If these deer were disturbed, for instance by cattle or sheep ranching activities, the mother would visit fawns less frequently. The question is then, what impact this has on growth and survival of the fawns. If disturbance has a major adverse impact, then it would be better to have ranching activities concentrated before or at least 2 weeks after the major birth month. And this is what we recommended to the ranchers, because at 2 weeks of age, these small fawns are no longer in hider mode and can easily outrun cattle and ranchers on horses, so that they can get out of the way of roundup activities. All that said, evolutionary relationships do play some role in milk composition. Dr. Amy Skibiel of Auburn and Harvard Universities and her colleagues looked at the effects of species ancestry, environment, and behavior on milk composition, using more advanced statistical techniques that take into account the non-independent relationships among species. They analyzed milk from egg-laying monotremes, pouched marsupials, and placental eutherian mammals across half of the mammalian orders, including 50 families and over 125 species. Dr. Skibiel's team found that ancestry and genetic relationships among species indeed influences milk composition. After controlling for this phylogenetic similarity in milk composition, Dr. Skibiel found that species that had a longer period of lactation had more dilute milk. This makes sense. Milk production is incredibly expensive metabolically, even more so than pregnancy. We can see that females with multiple infants or large, strong infants deplete their own body condition as they lactate, especially toward the time of weaning. It would be even more expensive if the milk in species with long maternal care and long lactation times was also high in protein and fat. Let's consider deer that live in different environments. A deer living in temperate forest will suckle its youngster for 240 days or so, with daily milk production of about 1 liter per day. And that milk has about 7.5% protein and 11.5% milk fat. Much more than a dairy cow, because deer fawns need to grow quickly to outrun predators. This composition is costly to the mother. Female deer may lose up to 15% of their body weight during the lactation period. Then they need to regain weight quickly in order to get pregnant and have other fawns the following year. A related animal, the reindeer, which has only a short period of Arctic summer to help its infant grow to a size which will prepare it for survival over the long Arctic winter, has energetically rich milk with over 10% protein and 22% milk fat, much greater in comparison with its temperate deer relatives. Diet also has a strong influence on the energetic density of milk. Carnivores make milk that is higher in protein and fats than milk of herbivores or omnivores. Atlantic gray seals, for instance, feed on fish, and their milk has over 11% protein an incredible 53% milk fat. They suckle their young for only 2 weeks after giving birth in seal rookeries in the subarctic during the cold spring. Young gray seals, who gain over 4 pounds of body weight per day on the rich milk, are able to quickly develop enough blubber to live on so that they can go to sea and feed on their own. The high protein and especially the high fat content are therefore an advantage to animals that live in cold seas and need to raise their large young quickly. Total milk synthesis, the volume produced during lactation, and how fat, proteins, and sugars, and even hormones in the milk change over the duration of lactation, are all going to be important as zoologists research milk composition and lactation in the future. And the results of these studies of milk synthesis will help us better understand ancestral relationships, behavior, and the ecology of mammalian species. Natural selection has shaped the milk production of mothers and the nursing behavior of infants, and those behaviors may be in conflict. The mother wants to grow her infants, but needs to consider her lifetime reproductive success, so needs to balance one infant's production and growth against the needs of the next infant. The infant cares about maximizing its own survival, so will take as much as it can get with little regard for its mother's own condition. How the mother makes milk using current body stores versus eating more varies across species, across individuals within species, and across seasons for each individual. Consider bears. Female bears of temperate species eat ravenously in late summer and early fall. Then enter a hibernation den where they will give birth to very small offspring, but will not have anything to eat, and then suckle the cubs in the dens for months before eating themselves. Bears are highly altricial at birth. The mother's ravenous eating behavior affects the composition of bear milk, and both the initial composition and changes over time during lactation are probably adapted to protect the small neonates from disease, to nourish these relatively immature offspring appropriately, and to support the maturation of the baby's digestive system. Our Chinese colleagues have found just this in their giant panda research. There appear to be 3 stages of lactation, with milk composition changing as the panda cub grows. Milk sugars are about 1.6%, low relative to sugar levels in cow and human milks, and decrease through lactation. Panda milk has about 7% protein and 10% milk fats 2 weeks postpartum. Milk fats and at least one significant sugar also change in percentage through lactation and relate to developmental needs of the panda cub. One sugar in particular followed the same increasing trajectory as cub weight gain. Pandas are bamboo-eating vegetarians, of course, and their offspring grow more slowly than other bears. Polar bears, in contrast, eat the blubber of seals. Zoologists have found that polar bear milk has 10% protein and 30% milk fat, so their cubs grow incredibly quickly. And it is in the female's interest to get the cubs out of the cold den and into the environment with her, so she can eat seals to help mitigate her loss of body condition while she lactates. Infants, meanwhile, need to ingest milk and metabolize it for growth, organ development, and behavioral activities. Infants first drink and metabolize colostrum, the mother's first milk that is produced in the days around birth. Colostrum has antibodies to protect the infant from disease through passive immunity, in addition to the proteins, fats, sugars, and other chemicals in natural milk. Colostrum is delivered in a concentrated, fairly low volume form for the immature and developing digestive system, and is a different color than milk. Then the milk changes through lactation, and the young develop their digestive system accordingly to metabolize it efficiently. So what this means for us zoologists is we need to consider how the mothers develop and deliver milk, and how the infant ingests and uses this milk, especially because we want to properly nourish both mothers and babies in our care in zoos. We need to consider the mother-infant behavior for frequency and duration of suckling, as well as how infants grow and behave while in the nursing stage of their lives. Much of the reliable data for most of this very reclusive behavior has been provided by zoo-based research, because we can focus cameras on zoo animals, making them easier to study. Besides protein, fat, and sugar, there are other bioactive components in milk that help the infant develop. And these include hormones and minerals that we haven't even discussed here. Milk scientists continue to learn about the chemical components of milk, and we can look forward to more to come from this important mammalian product, because we haven't even yet analyzed the milk of thousands of species. We can also learn a lot about evolution from studying milk. Species living in the same environment with the same diet and other factors may have different milk composition because they evolved from different ancestors. Or different populations of a species may move into different environments where they have different diets and different anti-predator needs or other factors, with important related changes in milk composition. So milk composition is one good marker of the historical pressures faced by ancestors, as well as current pressures faced by lactating females. Zoologists believe that the evolution of lactation has facilitated a remarkable increase in the sophistication of mammalian teeth. Nutrition through a mother's milk in infant suckling postpones the time at which teeth need to erupt to handle adult food. This lactation delays the need for teeth until much of the relatively rapid jaw growth is complete. So this might have been a precondition for the complex occlusion of teeth in the upper and lower jaws that is necessary for chewing and that is so characteristic of mammals. Teeth are important structures that co-evolve with our diet, whether we are herbivores, omnivores, or carnivores. Our adult teeth consist of an enamel covering over a relatively soft core of dentine, and in most mammal species, teeth stop growing once their owners are adults. In elephants, mammals that are so huge that they take years to grow, there are special modifications for adult tooth eruption. Elephant milk has 15% fat and 5% protein, and baby elephants are weaned pretty slowly, switching completely from milk to grasses and leaves, sometimes between 3 and 5 years of age. This is reflected in their tooth and jaw development. It may take over 20 years for an elephant's jaw to reach full size. Throughout an elephant's growth, their brick-sized molars erupt sequentially, one at a time from the rear of the jaw, about one tooth every 10 years on average, more frequently earlier in life and then slowing down with age. Beavers live to be 24 years old or older and are famous for their chewing abilities. Zoologists have found out that beaver kits nurse up to 9 times daily, about once every 2 hours, for only 60 days, and the milk has about 12% protein content. Kits start eating leafy material at about 10 days of age and eat substantial solid food at 1 month of age as suckling declines. Deciduous premolars are shed and replaced by adult molariform teeth at about 11 months of age. Clearly, nursing and jaw growth are in delicate balance so young mammals can receive nutrition and care from their mothers as they become physically dependent and fend for themselves by eating solid food. Almost 1/4 of our world's mammals are considered to be threatened with extinction by the International Union for Conservation of Nature mammalogists. And we know that over 75 mammals have gone completely extinct in the last 500 years. Habitat loss now affects almost half of all mammals globally, while the second greatest threat to mammals has been poaching for parts and bushmeat. We have learned historically that endangered mammals like bison, wolves, and black-footed ferrets can come back from the brink if we give them ample habitat and protection from overhunting. If you have a chance, which mammal will you help to save?